Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class, we were discussing about various discrete choice models. So, we'll be continuing the discussion in that direction today also. So, today we'll be discussing an important concept called satisfaction function in the discrete choice models. So, satisfaction S is a scalar that captures the expected utility that an individual derives from a set of alternatives. Suppose that set is denoted by k here, and each alternative has an utility uk. Okay. So, it is the expected utility that an individual derives from a set of alternatives. Okay. Now, since each individual is assumed to select the alternative with the maximum utility, the satisfaction is simply the expectation of the maximum utility alternative. Okay. So, this is the assumption that we make in the discrete choice models, that every individual will be selecting the alternative that offers the maximum utility or attractiveness. Okay. And that is why the satisfaction is simply the expectation of the maximum utility alternative. Okay. So, why are we discussing this satisfaction function? Because this will be required when we will be discussing the optimization formulation of stochastic user equilibrium. Okay. So, all of this discussion that we are doing from the last few lectures is actually to move towards the development of stochastic user equilibrium optimization formulation. So, before we can actually go there, we are revisiting some important concepts of discrete choice models. So, to mathematically represent this satisfaction function, we say that it is the expected value of the maximum utility that we get among all the alternatives. Okay. So, this is what we have. So, the max is over all the alternatives k. So, the maximum utility that we perceive from any alternative, that this value, and we take the expected value of that. Okay. So, in a way, this satisfaction function is slightly different from the choice probability function that we had seen. So, the choice probability of the kth alternative was the probability that a given choice k will be selected. Okay. So, that was equal to the probability that the utility of that alternative being greater than or equal to the utility of all the alternatives. Okay. So, we take the probability of that case, that the utility of the given alternative is greater than or equal to the utility of all the other alternatives. Whereas, here we are trying to find the expected value of the maximum utility among all the alternatives. Okay. Now, if you remember, in discrete choice models, we are aware of what is the systematic component or the systematic utilities that we have. Okay, these are the measured utilities or the deterministic component of the utility that we can say. So, this is represented by this vector v here. A is this set of attributes that we had discussed before. So, this is given to us. Okay, so these are given values. We are also aware of what is the distribution of the error terms, which is denoted by this bold vector here. Okay. So, given that we have knowledge of these expected or the measured or the systematic components of different utilities v and the distribution of the error terms, the satisfaction function can be expressed as a function of the vector of measured utilities v as follows. So, what we are doing here is that instead of uk, we have replaced it with vk plus the error term corresponding to this kth alternative. Okay. Now, we will be stating some important properties of the satisfaction function. Although we will not be looking at the derivation of these properties, but it is important to mention these properties because these properties actually also define the properties of the objective function of the stochastic user equilibrium formulation that we will see later. Okay. So, for example, in the normal deterministic user equilibrium case, we had argued some properties that the objective function is strictly convex and so on. And in order to do that, if you remember, we had some assumptions on the travel time and so on. So, in order to also be able to argue that the solution that is obtained from the stochastic user equilibrium formulation is unique and so on, we will be requiring some properties and so on. Okay. Okay, so the first property that is there is that the satisfaction function is convex with respect to the systematic utility vector V. Okay. Okay. We are not going into the derivation of this, but um, the idea behind this is that um, the max operator, since max is also a function, max function is actually a convex function. Okay, so it is not very difficult to actually derive this property. Okay, so since we have seen that satisfaction function can be written as a function of the expected utilities as we saw in the last slide, so this property can actually be derived. Okay, but for the sake of time we will not be discussing that. Another important property that is there is that the partial derivative of the satisfaction function with respect to the systematic utility of an alternative equals to the choice probability of that alternative. So that means that if you take the partial derivative of this s with respect to the systematic utility of kth alternative, so it is equal to the probability of choosing that kth alternative. Okay. So this property actually connects how the choice probability is connected with the satisfaction function. Okay. And the last property that is there is that the satisfaction function is monotonic with respect to the size of the choice set. What does that mean? Is that if suppose we have a set of k alternatives whose systematic utilities are given by V1 till Vk here, and suppose we consider another modified set now where we have one more alternative, okay, k plus 1. So now we have added the systematic utility component of this alternative also. So with this new set here, which is kind of a superset of the original set of k alternatives, the satisfaction function will be larger than or equal to the satisfaction function of this. Okay, this is also kind of intuitive in the sense that since satisfaction function is taking the expected value of the maximum alternative utility, so if you are adding one more alternative, so the satisfaction function can only increase or stay the same. Okay, but again we are not going into the rigorous proof of this definition here for the sake of time. Okay, so for logit models, the form of the satisfaction function can be explicitly derived from the second property. So if you recall, for logit choice models we had closed form expression of the choice probability. Okay, unlike the case when we were discussing about multinomial probit models where the choice probability function does not have a closed form expression, we have a closed form expression for the choice probability when we are focusing on logit model. Okay, so this is that expression. So we have seen this before. Okay, so this is written in terms of the systematic utilities of different alternatives. Okay, so with this actually it is possible to derive the satisfaction function. Okay, so the satisfaction function actually comes out to be this. It is ln of this summation of e to the power vl, where this L is going over all the alternatives. Okay, and in order to derive this, what we require is this relation, and we require one more boundary condition, that the satisfaction value will be equal to the systematic utility of the kth alternative if the systematic utilities of all the other alternatives tend to minus infinity. Okay, so let us just see what is this boundary condition. So this boundary condition is very easy to understand. So if the systematic utilities of all the alternatives are going to minus infinity except the kth alternative, so since this satisfaction function is the expected value of the max of Vk plus this error term here, so then you can understand that the max value actually will then correspond to this kth alternative. Okay, Vk plus Ek, because for all the other alternatives the systematic utilities are going to minus infinity. Okay, and so this will be equal to then the expected value of Vk plus this error term for the kth alternative, and this can be written as the expected value of Vk plus the expected value of this error term for the kth alternative. Okay. Now, if you recall, we assume that the expected value of the error term is equal to 0. Okay. So, therefore, this will be equal to the expected value of the kth alternative, and since the systematic utility is a deterministic component, so the expected value is equal to Vk. Okay. So, this is the basis for having this boundary condition. Okay. So, let us see how we can derive this expression using this relation and this boundary condition. So, let us take x is equal to the summation e to the power Vl over all L. Okay. Now, if we take dx by dvk, so this will be equal to e to the power Vk. Okay. So, then dx is equal to e to the power Vk times dvk. Okay. So, therefore, this relationship can be written as this derivative with respect to the satisfaction function equal to dx by x here. Okay. And then we take integrals on both the sides. So, we get the satisfaction function is equal to ln x plus some constant, where this x is equal to summation e to the power Vl plus constant. Okay. Now, we can apply this boundary condition that s is equal to Vk when Vl goes to minus infinity for all the other alternatives. So, in that case, this is equal to Vk, and if Vl is going to minus infinity for all the alternatives, we will have ln of just Vk here, because all the other terms e to the power Vl, if L is not equal to k, will be equal to 0. Okay, plus constant, and this thing is equal to Vk plus constant. So, Vk gets cancelled and we get constant equal to 0. Okay, therefore, what we get here is that the satisfaction function is equal to ln e to the power of Vl and this summation here. Okay. So, that is how we get the satisfaction function. Okay. So, for probit model, the satisfaction function cannot be expressed analytically, and thus requires numerical methods like Monte Carlo simulation to compute it. So, if you remember, in the last class we had seen how we can use Monte Carlo simulation to determine the choice probability for probit model, because it is not possible to determine that in a closed form expression like the logit model. So, let us now see how we can determine the satisfaction value for the probit model. So, the utility of the chosen alternative un is recorded at every iteration. Okay. So, if you remember, what we do in the every step of Monte Carlo iteration is that we anyway have the systematic utilities, and we derive a sample of the error terms from the distribution that we have. Okay. So, we get the values of Vk plus the error term for each alternative. Okay, because this is anyway given, and this is a value which has been derived from the or obtained from the distribution of the error term. Okay. So, with this we will be getting the systematic utility of each alternative, and then we can find out which alternative has the highest utility. Okay. So, if at the nth iteration of this algorithm, if un is the utility that we record, that is the utility of the highest alternative, and if we sum that across all the iterations of this Monte Carlo and divide it by the number of iterations, this is the satisfaction function we get here. Okay. So, now why is this symbol being put here? This is telling that this is approximately equal to this expression, and this will be exactly equal to this only when the this capital N, the number of iterations, goes to infinity. Okay, that is why this symbol has been written here. Okay, so with this we have completed the discussion of satisfaction function. So now we will be moving towards route choice, that is how do we use these discrete choice models in the context of traffic assignment. So, network loading is the process of assigning the OD entries to the network for specific link travel times, that is constant link travel times. So the process follows the route choice criterion which underlines any traffic assignment model. So if you remember that in deterministic user equilibrium problem, we had this step of all or nothing assignment when we were solving it using convex combination method. Okay. So what we used to do in that step is that we had the information of the link travel times given to us, and those were constant link travel times. Okay, and based on those link travel times, we had to assign the flow to the network. That is, for every origin destination pair, there was travel demand given to us, and we had to assign that demand to various paths connecting that OD pair. Okay, so that is what we had seen as the network loading for the deterministic models. Okay. So this is what it is saying. The deterministic user equilibrium model assumes that each alternative follows the path with the shortest travel time from origin to destination. Okay. So this is the standard assumption of the deterministic user equilibrium model. So therefore, the network loading mechanism underlying the deterministic user equilibrium assignment can be modeled by an all or nothing assignment process, in which each OD flow is assigned to the shortest travel time path connecting this OD pair. Okay. So this is what I had said, so all or nothing assignment. For every OD pair, we assign all the flow to the path that has the shortest travel time. Okay. So for example, convex combination algorithm, we had used this all or nothing assignment procedure. Okay. So now the question is that what is the counterpart for this all or nothing assignment when we have stochastic travel times? And also one more thing to highlight is that the deterministic user equilibrium model results from the coupling of this assumption with the dependence between travel time and flow. Now what is this saying? So when we are doing this all or nothing assignment, we are assuming constant travel times. Okay, so in that step, we do not assume that the travel time is the function of the flow. However, that is just one step of this method of convex combination that we are using to find the user equilibrium solution. So we have to have some step that actually relates the travel time with the flow also. Okay, so that is why if you remember, once we do this step of the all or nothing assignment, we get the flows across the network, and then we had a move size step after that, and then we got the new solution xn plus 1. Okay, now this new solution, if we go to the next iteration, given that the termination is not reached, then we again input that into the travel time function. Okay, so that step actually relates this coupling between the travel time and the link flows. Okay, so even though in the network loading model we are not relating the travel times with the flow, but in the overall framework of the user equilibrium, when we are trying to find the solution using convex combination, there are other steps where the travel time gets affected by the flow. Okay, so we now formulate a network loading model that is more general than the all or nothing assignment. So this model views the route choice in the framework of random utility and discrete choice models. So one thing to mention here is that all of this discussion that we are doing of stochastic user equilibrium that we will be finally moving to, so this is for the case when there is some uncertainty in the travel times. Okay, if the uncertainty is 0, then everything becomes equivalent to the discrete user equilibrium problem. Okay, so that is why this discussion, this framework that we will be developing for the stochastic user equilibrium, this will be more general than the framework that we had developed for the deterministic user equilibrium. Okay, so if we have all the error terms to be equal to 0 in this framework, then it will be exactly be equal to the user equilibrium formulation when it is a deterministic case. Okay, so we will be focusing on this network loading mechanism, which is referred to as the stochastic network loading. So this will be an extension of the deterministic network loading process called all or nothing assignment that we had seen. So in this model, the dependence of the link travel time on the link flows is not treated here. Okay, in order to concentrate on network loading when the path travel times are random. Okay. So, like in the case of all or nothing assignment, if you remember, uh, we have constant link travel times, and based on that we assign the flow. Okay. So in that step we are not worried that if, for example, everyone decides to take a particular path, then the travel time will change. No, that's not the case. The travel time is fixed for every link, and therefore it is also fixed for every path. Okay. So same in this case also, in this stochastic network loading also, we will be assuming that the link travel times are stochastic, but they are not function of the link flow. Okay. But since we will be finally going on the stochastic user equilibrium case, this dependence of the travel time on the link flow will eventually come. Okay, just now for the understanding of the stochastic network loading model, we are not considering that aspect where the travel time is the function of the flow. Okay, so this is what it is saying. The equilibrium effects in conjugation with stochastic network loading will be discussed later. Okay, after a few lectures. So let us consider a population of drivers who are about to take a trip between a given origin and a given destination. Okay. So the OD pair under consideration is connected by many alternative paths, each associated with some travel time. Okay. Now, due to the variations in the perception and some exogenous factors such as weather, lightning, etc., the path travel times are perceived differently by each traveler. Okay. So now we are kind of providing the motivation for having random travel time. So, for example, if there is a population of people who want to go from same place A to place B, what this is being said here is that not everyone might perceive exactly the same travel time for every path. Okay, for example, if there are two paths connecting place A to place B, path 1 and path 2. Now, first individual might think that uh, suppose the path 1 has a travel time of say 10 units, but the path 2 might have the travel time of 20 units. So he will then choose path 1, but the second traveler or the second individual might not perceive the same travel times because he might be having different perception. There might be uncertainty of the information. So he might, for example, assume that suppose the travel time of the first path is say 16 units and the travel time of the second path is say 10 units. So in that case, he'll be taking the second path. Okay. So because there is some uncertainty in the travel time, so the travel times that are perceived by different individuals need not be same. Okay. Therefore, the perceived travel time of each path is modeled as a random variable that is distributed across the population of travelers. Okay. So if we assume that the perceived travel time of each path is a random variable, so it will have some distribution. So every time, for example, a traveler comes and he has to travel from a place A to place B, so we will be randomly picking one value from that distribution, and whatever value that comes out is the travel time that is perceived by that traveler. Okay. So that's why, since these travel times of different paths are perceived to be differently by different travelers, so not everyone may decide to take the same path because not everyone might perceive the same path to be the shortest. Okay. So given his or her perception of the travel time, each driver is assumed to choose the shortest travel time path from origin to destination. Okay. Now each driver, however, will perceive path travel times differently because the path travel times are coming from a random distribution. So anytime when you pick a value from the random distribution, it need not be the same exact value, it can be having different values. Okay, and therefore each driver may choose a different path. Okay. Now since the perceived travel time of each path is a random variable, it is associated with some probability density function. Okay. So this probability density function gives the probability that a driver randomly drawn from the population will associate a given travel time with that path. Okay. So there is a travel time distribution for every path. Okay, so that distribution actually kind of defines that if we have an individual or traveler from population, so um, the travel time that he might experience will be a random value from that distribution. Okay, so the stochastic network loading problem is to determine based on this distribution how many travelers will use each path. Okay, now what we can do here is that since we can obtain this probability of using these different paths, because that will be equal to the probability that the perceived travel time on a given path is less than the perceived travel time on all the other paths. Therefore, in that way, one can determine the path flows for different paths. For example, if there are two paths connecting a place A to place B, so since we can uh, determine the probability that the travel time on a given path may be perceived to be lower than the travel time on any given path, we can actually determine the path flows for different paths. For example, suppose the probability that the perceived travel time on the first path is less than the perceived travel time on the second path is 0.4. Okay, and similarly the perceived travel time on the second path is lower than the perceived travel time on the first path, that probability is suppose 0.6. Okay, so then if suppose 100 people want to travel from A to B, then the flow that will be assigned to the uh, first path will be 100 times 0.4, that is 40, and the flow that will be assigned to the second path will be 100 times 0.6 equal to 60. Okay, so in that way we can get the different path flows for different origin destination pairs. Okay, now once we have obtained all the path flows, we can obtain the link flows also. Okay, by using these incidence relationship that we have seen before. If you remember, we had this xa is equal to this triple summation FKRS delta AKRS. Okay, so that is how the path flows are related with the link flows. So once we are able to find the path flows, we can determine the link flows also. Okay, so let CKRS represent the perceived travel time in path K connecting origin R and destination S. Okay, so we assume that CKRS is a random variable. Okay, and also let's this small CKRS be the measure or the actual travel time on path K connecting between R and S. Okay, and we'll be assuming that the CKRS is equal to this perceived travel time on path K is equal to the measured travel time plus this error term. Okay, and we'll be assuming that the expected value of this error term is equal to 0. Okay, and therefore the expected value of this perceived utility will be equal to this. Okay, so this we have seen before, so we can take the expectation function on both the sides, and since the expectation of this error term is equal to 0, the expectation of this will be equal to the expectation of this, but since this measured quantity is deterministic, so this will be equal to that. So that is the average perceived travel time is the actual travel time. Okay, so with this we'll be ending today's lecture, and we'll be continuing in the next class. Thank you.